Okay. This week we'll talk about the introduction to feedback control system. Okay. The objectives of this study are, first of all, we need to propose the appropriate model for the PID control algorithms. Anyone knows the PID algorithm? You can write the chat. And after all, we need to design desired PID based on transfer function. Block diagram and other methods. Okay, these are objective, and so in order to design your system in terms of the control perspective, we need to utilize the sum rules based on the sum control theory algorithm. But first of all, we need to design or define two terms: the closed loop and open loop concepts in control. Okay. Does anyone know anything about the closed loop control? Anyone knows that? First of all, we need to propose a system in here. We have a system like this one. And so we can assign to the x, c, k, and ft can be applied to the system. Okay, and so we need to give the f equals to the mx dot plus c x dot plus kx. This is our equation of motion related to this dynamic. And so after all, if we take or obtain the transfer function of these terms in terms of the xs divided by fs, which is equals to the in the Laplace domain 1 divided by ms square plus cs plus k. Okay, this is our term. And so how we can design or define this system in the block diagram? Just remember that if we have the block diagram, we can draw this kind of structure. First of all, we have a plant in here in terms of the gs, and so we can drive the ms squared cs plus k. Okay, and so this generates to the xs, right? And so what is the input of this system? Can anyone say that? What's the input of this system? Yes. Thank you, İşcan. Fs. So this is Fs. But in order to measure this value, and so we need to apply to the some other transformation in here, just like this one. This is the Hs, but we call it in real life. This is equal to the sensor. Okay. And so this sensor is feeding into some another parameters in here, minus term, and also we feed to the RS signal in terms of this is the reference signal. Okay, we call it, and so we have a desired x value or the meter or the position values we feed it in here, and so this XS can be measured by using what the sensors in here, just like this one. This is the sensor, and so sensor has also a modeling in here, and so this is the continuous plant, okay. And also we need to drive these algorithms in here. This is the error signal, because the reference minus the our current position gives us the error for a desired position. And so how we can condition this system? We set another block in here which is designed by ourselves. We should call it to the what? The CS. And also this is, for example, a driver. Okay? But driver has also time dependency or time properties based on these informations. And so how we can call it this system? This is a closed loop control system, because this XS is measured by using the sensor, which is defined in the HS, and so we can convert this value into the reference signal. And so reference signal minus XS gives us the error, and so we want to minimize this error value in terms of the what? The FS. And so we will select the proper FS based on the what? The designed CS value. This is the controller or the driver. Okay. Also, this is the feedback. Just remember that. And so, if in the general notation, if we have feedback or measured signals in here, and we can say that this is closed loop. Okay, this is closed loop. And so how we can model these values in here? First of all, X in the block diagram, which is equal to what? G times C times this one, the error signal. Error signal is created with what? The R minus, this is coming from this one, X H times X. Okay? And so if you recollect the whole X term at the left hand side, we will have to the what? To this one. 1 plus C H G, which is equal to what? R C G. Okay? And so how we can define the closed loop total dynamics for a given the reference signal in here? XS divided by RS, which is equal to the what? C times G plus C H G. This is what? The closed loop. This is closed loop transfer function. Okay. These are the bases. And so if you want to design the specific pole or the characteristic equation in here based on what? 1 plus CHG, we need to set or design the proper C coefficients with the basis of what? The proportional, integral, and the derivative controller techniques. Okay. So this is the closed loop one. And also we have the open loop control in here. It's rare, but it's efficient method for the control systems. Open loop control. Okay. So suppose that we have a system. We have this kind of system. Xref S. This is the reference signal. And also we have this kind of body in here, just like this one. 1 plus S plus 1. These are planets. Okay. And so this generates what? The XS in here. And so we need to design the some specific block to what? To fit the FS value in here. But we don't know what is the value or the transfer function of this controller signal in here. And so in the control theory, in the control, the main purpose is x is equals to the xref. This is called reference tracking problem in the literature. If you want to drive the system to the reference signal, how we can accomplish these values? And so we can assign the new variable in here, cs. We need to design it, but how we can do that? In order to satisfy this condition, we can say that xref times cs times 1 divided by s plus 1 must be equal to the xs. See, this is the first one. And the second one, if this is the R equation, the R condition is that, and so xs must be equal to the xrefs. But how we can change the dynamic of these terms? See that in order to satisfy this condition, xs divided by xrefs must be equal to the 1. And so how we can collect these terms? The cs times 1 divided by s plus 1 must be equal to the 1. And so due to this condition, the cs must be equal to the s plus 1. See, this is our controller. But this is open loop controller. If we select or design the s plus 1 in here, and so we can control this system, but we don't have any feedback in here. Okay? Because we cannot measure the access value without the sensor or any other feedback conditions in here. Okay? So this can be useful, but in the literature or in the applications we will use mostly the closed loop control systems. Okay. So any question? There's no questions, and so we need to give what the general structure of the water controller approaches. The general framework for control system contains these block diagrams. First of all, we have the GPS. These are plant or physical systems, guys. Okay, and so this system generates to the CS. This is the controlled signal. Okay, for example, R position, R velocity, R theta value. Okay, and so in order to apply this GPS, we need to define to the actuation signal, but with some disturbance value. You don't need to know this disturbance right now, but it's important parameter. The disturbance can be applied for this system in the general control approaches. Okay, for example, if you want to design the position control for the DC motor, for example, we may have the static friction, which is called the disturbance, because we don't have any model about it. Okay, and so we can assign as a disturbance value because it directly affects or creates the torque value, but we don't know the model, and so we can assign it as a disturbance value. In the general structure, the MS or the actuation signals can be given in here. In the DC motor, for example, this must be equals to the what? Equals to the torque value. Okay, and so how about this? In order to create the torque value or the actuation signal, we must utilize the GAS. This is the actuator dynamic. Okay, and so the control signals must also be given in here, but this control signal is a virtual signal. Control signal. And so this can be calculated based on what the microcontroller or any other processor, just like this one, GS, the controller. And so we need to design this controller signal in here, but this controller signal must be fed with the what? With the error signal in here, because we want to minimize the error value with the what? With the C and the reference signal. And so if this is the case, how we can calculate the error signal in here? Positive and negative values can be given in here, just like this one. And so RS must be given in here. This is the reference. And so we have also HS, the sensor dynamic in here. And so this sensor dynamic can be obtained from this one. This is what? This is the sensor. Okay. In the system dynamic and the control theory, we have these general controller approaches to what? To design your system based on the what? This proposed model. Okay. And so if we want to design or analyze these signals or these controllers, we need to what? Apply the transfer function formation, just like before we did. For example, in order to model this closed-loop signal with respect to what? The C divided by RS, and so we need to obtain the closed-loop transfer function formation in here. First of all, we have in the first place the C signal in here, just like this one. And so C is a combination of the what? The GP times. And so we have a disturbance value as a negative value in here, minus D, plus GA times EC times. And so we have also error signal in here, R minus H times C. Okay. These are the basic solution for what? For the transfer function formation. And so if we expand the whole equations in here, we will have this kind of formation: R times GP times EC times EA minus D GP, which is equals to what? The C times 1 plus H EC GA GP. Okay, this is the solution or the reorganization, the equation of these terms. Okay, and so if we have the C value here, and then we can say that this is equals to what? The C R times GP times EC GA divided by 1 plus H GC GA GP minus D GP 1 plus H GC GA GP. Okay. This is our closed loop transfer function nomination modeling in here, but in this case this disturbance cannot be modeled at every case, and so we can assign this value as equals to the 0 because we don't have any modeling in here. If we simplify the R system returning into the what? Into this position, CS divided by RS, which is equals to the what? GP GC GA divided by 1 plus H GC GP GA. This is our basic transfer function for a closed-loop system analysis, because we don't have any model about the disturbance value. But if you have the modeling with respect to the what? The disturbance value, you can use this general form. But generally, we use this kind of conditions. And after that, we should design our controller based on the what? The characteristic equation, the denominator of this transfer function. Okay? Any question? So If there is no question, and then we will continue with what the 10.3 modeling control system. Okay. First of all, we need to design what the sensor and actuator modeling, because the actuator and the sensor modeling are in the form of the time domain, because we have the dynamics in here. For example, if you want to utilize what the DC motor has its own time dynamic or the equation of motion with respect to what the Laplace domain, and sensor also have this kind of properties in here. Now, for example, the feedback control system can be given by with this plant formation. First of all, we need to drive the block diagram in here just like this one. K divided by tau s plus 1. These are the plants, okay? The continuous dynamic. And so we will feed the what the CS in here. And also, just remember the previous slide, we have the DS, disturbance value, and we have also a actuator dynamic. Okay? The actuator dynamic is just kind of the plant. It has the time constant and some proportional coefficients Ta, tau A plus S1. Okay? And also we have some virtual signal, the Fs in here, just like this one. And also we can give the Kp as a control coefficient in here. And also we should feed the error signal in here, just like this one. And Rs must be fed in here, and also minus, we need to obtain the equation of motion of the sensor dynamic in here, which is in terms of the transfer function Ts sensor tau s plus 1. Okay, these are the basics for the sensor, actuator, and the plant dynamic in here. In the real life, we must use this kind of properties in order to model the R system based on the system dynamics property. Okay, because the R actuator and the sensor has also a dynamic to generate the voltage value or the force value. You should remember that. Okay, but we have some important property in here. The tau is the plant tau, must be greater than tau actuator, and tau actuator must be greater than tau s. And so this is the fastest signal, this is the fast signal, this is the slow signal in here. And so what's the importance of this condition? Just remember that if you have a system with the tau value of 1, in order to sample or drive this signal, this tau, actuator tau, must be smaller than this one, because we want to control this system based on the time dynamic, which means that if we have the tau value, at least the actuator dynamic or the tau value must 10 times smaller than this tau value. And so we can see and we can drive this system based on this information. But if we want to do this, our sensor sampling time must be slowest one with with respect to the system, because if we want to sampling this system, for example, the tau is 1, but if we are using the 0.1 tau in here, and so we cannot see or measure the signal changing in here. So this condition must be satisfied to the to control the R signal. And so how we can obtain this value? We need to use this directly relates to the response time. Okay, and so this response time can be obtained with the actuator catalog value or sensor catalog value. Okay, And so, since we can control the system, sensor actuator must be faster than the plant. Okay? Especially for the root locations affecting the oscillation or the root divergence. Just remember the previous lesson. Sensor and actuator dimension will change the response of the system. But in the ideal condition, sensor must be equal to the 1 is equal to the 1, actuator is equal to 1. But in real life, we don't have such kind of property. And so this general structure are most valuable part for the what? For real-time application. And so how we can prove that? Just see that we have the examples in here. Suppose that we have the RS signal in here, plus, minus, and we can assign the proportional coefficients in here in order to derive what the R actuator. And R actuator, tau S1, and also we can assign what 1 divided by 2S plus 1. These are the plant, and so this generates what the CS. And also we have ideal sensor measurement, which means that if we obtain or measure the C, we have the complete value, the exact values of the CS. We don't have the dynamics in here. And so how we can calculate the what? First of all, the closed-loop transfer function in here. First of all, we need to say that the C is equal to the what? This is the G. This is the what? G. Find the roots of these terms. This is the what? A, for example. This is the what? This is the, for example, the Z. Okay. And so C must be equal to what? The G times A times Z times R minus C. Okay. And so we can reorganize the whole equations in here with the basis of what? These terms. But in order to solve this equation easily, we can collect this Z, A, G terms into the one term, just like this one. GS is equal to what? The KP is the constant coefficient with the multiplication form, and so tau S plus 1 times 2S plus 1. These are the what? The collective form of these terms, the GS. Okay, and so in order to create the what? The closed loop dynamic, and so we can write that R minus C times G is equal to the C. And so our transfer function or the closed loop transfer function CS divided by RS is equal to what? The G plus 1 divided by G. And so this can be equalized with the what? TS, and so the TS is assigned with the what? Or after the calculation KP 2 times tau A S squared plus tau A plus 2S plus KP plus 1. Okay. So first of all, we need to say that if the tau A or the actuator dynamic is cancelled in here, tau A is 0, and so the TS value, this term removes, we have this information in here for the transfer function KP divided by 2 plus S plus KP plus 1 divided by 2. Okay? If the actuation mechanism or the dynamics is removed or cancelled, and so tau A is equal to 0, we have this kind of information or the transfer function. And so what is the root of this term? The root of this term is equal to what? Minus KP plus 1 divided by 2. Okay? And so we can set the different different root values at the characteristic equation with the basis of the selection of the KP value in here. But if we want to use the tau A, time constant A, tau A as equal to 0.02, okay, and so we will have what? The transfer function just like this one. We just put the tau A into the what? This equation, And so 25 kp divided by s square plus 101 divided by 2 s plus 25 kp plus 25. Okay, so what's the root of this term? We have now the two roots instead of what to 1. This is the first place, right? This is the one root, but we have two roots, and so this root is equal to what? Square formulation. We have 9801 and 400 kp in here divided by 4. See that this is the first one, this is the second one, and so these two systems are real but are the same. But in this case, we have some basic differences between the roots. See, if we are using the ideal model, we should know that the R sensor ideal sampling time, ideal value, coefficient value, and ideal measurement values. We must be sure about that. And so we can use the condition of the one. But if we don't know anything about this one, the second rule must be utilized in order to assign to the what the system property into the what into the specific characteristic equation pose with the selection of the what the kp. Okay. This must be remembered in this case. Okay, any question? If there's no question, and so we will continue with this one. 10.3.3 modeling DC motor control. Okay, first of all, we need to drive the sham of the what the DC motor modeling. The sham is given by with this one. First of all, we have a model in here as a motor. Okay, this is our motor, and so we have the what the inertia values of these terms, just like this one. And so just remember the previous lesson, we have the what the tooths in here, the solid rock, and also we convert the values of these terms with the what with the load value. Okay, and also we assign to the what the tachometer in here in order to what obtain the position of these terms. Okay, this is the tachometer, this is the load. Okay, and so if we have this one, and so torque load and wheel load is given in here, and also Wm the speed of these terms and torque M can be designed with this one. And so we have the ratio, tooth ratio in terms of what? In terms of the okay. And so in order to drive this in the what in the real life, we need to connect these terms in the electrical information. We can assign to the what to the amplifier, right? And so this amplifier is utilized with the what with the controller perspective, and also we need to design the other elements in here just like this one. Multiplier is utilized to what condition this amplifier, that's the K1. And also we need to define to the what the error signals in here, and which means that this error signals is equal to what is utilized with the comparator signals in the real-time applications. Okay, we must use the multiplier, amplifier, and comparator, and so this comparator is assigned with the what with the specific RPM value for the motor velocity. okay, W ref signal, okay. And so this comparator also should be fit with the what? With the tachometer value. This is the real description for the what? For our system. And also we should say that for the tachometer, we need to say that the V tach is equals to the what? The key tach. This is the proportional value to generate the what? The voltage values with respect to the what? The WL, okay. And so also V port can be utilized or converted in here just like this one, the KD times K port times V R, okay. See, this is the reference signal. V port can be generated in here. V tach is generated from the what? From the tachometer in here, just like this one. And so in order to simplify the R calculation, K tach must be equalized with what? The KD and K port. Okay. K tach is equals to the what? The KD times K port, in order to simplify the R algorithms. And so here, in order to generate, first of all, the error voltage, we should write the VE. This is the comparator error voltage value, KD times K port times V reference value minus K tach times WL, okay. And so in the second place, the motor model can be given by with the what? The A is equals to what? The IM plus IL plus I tachometer divided by N square. This is the tachometer inertia, this is the load inertia, and so we have a truth value in here, and so this is equalized with the what? With this one. And also we have the what? The CE, C divided by N square, because we have also a friction in the what? In the load model in here. And after that, we should write to the what? To this one. At the 3, we have IE dW and dt must be equal to what? The torque M is coming from the electrical power of the motor and torque load divided by N minus CE W M. Okay? And so in the S domain, we will have to the what? The IE SWM, which is equal to the torque M minus torque load divided by N minus CEWM. And so if we recollect the whole equation, we can write the WMS in terms of the what? This one, 1 divided by IE S plus CE times torque M motor and torque load S divided by N. Okay, these are the transfer function to generate what? The specific velocity value at the angular speed of the disk motor. And so just remember that this is what? Right now this is the disturbance value. See, this is the disturbance, and this is the what? The input, and also this is what? This is the output. Okay. These are the basic information about how we can model the, in the real life we have this mechanism, and the real, in the mathematical models we have this output, input and disturbance values of disturbance. But how we can convert these values into the block diagram? Just see that. In this case, the 4 is equals to what? The block diagram is to what? First of all, we need to assign to the what? The 1 divided by L, omega L, torque load, which is given in here, and also we have the omega M. This is what? The WM, which is fitted with the what? 1 divided by E times S plus CE. And this is fed with the what? The minus and plus, and so this is 1 divided by N, and this is the torque L. and so torque M is given in here, and this torque M is converted with what, a KT times I value, and also we have the A in here, and so this A is generated with what, 1 divided by LAS plus RA. This is the DC motor electrical models, okay? And also we should give what, the back EMF signals in here with the what, with the KB coefficients, okay? So after that we must provide the KA and K1 values in here, because we need to give the what, the specific position value, and so this must be converted with the what, with another signals in here for the VA, just like this one. And so KB is the comparator, and the what, the amplifier coefficients in here, and so this VA is generated with the what, this is the plus term and this is the minus term, and so this minus is given with the what, with the K tachometer in here, and so this tachometer is obtained from the load velocity, angular velocity values, and so the reference signal is feeding with what, the K port and KD value, okay? And so this must be given with what, the reference R or the omega values, okay? And so K tag must be defined in here. This is the real depiction of the what, the R algorithm in terms of the what, the real-time application. But this is too complex to analyze it. How we can simplify this algorithm in the file? Suppose that if we have any induction or any kind of induction cannot happen in here, LA can be equalized with the 0. And also K port times KD must be assigned with what, the K tachometer in here, and torque load can be considered as a torque load is equal to what, to the 0 value, okay? These are the conditions, okay? And so in this case our system converted into the what, the reference as signal plus minus term, and so also we can give the what, the KP controller coefficients in here, and also the previous block diagram can be written just like this one, KT divided by N divided by RA times IPS plus this one RA times CE plus KT times KB, okay? These are the basic equation for what, the torque load S values of these terms, okay? Or we can define the general I value, N times RA times IE divided by KT, and also C can be defined by the N RA CE plus KT KB divided by KT, okay? These are the basic generalized I and C coefficients, and so this diagram turns into the what, into this simplest form. Omega this term, and also the EGS, and also we can write 1 divided by IS plus C, and the R equation turns into the what, into this, okay? This is the ideal form of the system, okay? But we have a problem in here, which is equals to what, how we can design DCS. In order to design this DCS, to what, to track this omega R is tracking omega L. How we can do that? We will implement this DCS block diagram in terms of the what? In terms of the PID control algorithms. Okay? In the next lesson, we will talk about it.